Moving beyond power functions, functions to a power, we can get into functions involving exponentials and logs, specifically exponentials with base e and the natural log. So we can do integrals involving that stuff too without any sort of crazy advanced technique. So because of our favorite differentiation formula, the derivative of e to the x is e to the x, we get a nice little integration formula that the integral of e to the x is also e to the x plus some constant. So if it's its own derivative, it's its own integral. So think again of the chain rule. If you have e to a function now, so imagine it's e to the x squared or something. The derivative of that, because of the chain rule, is e to the x squared times the derivative of x squared. So in that case, it'd be e to the x squared times 2x. So now we want to do that backwards. So if you look at the thing on the right-hand side, if you see an integral that has that form, we can basically do a u substitution like we did before and put it back together. Okay, so the easier way to write that is so that whole thing, u prime of x dx is just like du. So if you have the integral of e to the x, that's just e to the x. But if it's e to some function and then times the derivative of that function with the differential in there, then it's basically the same thing. You just have a function for u instead of just a variable. For example. So again, when you see something like this, don't think there's some kind of product rule. This is a product of two things, but that's not how it works with integration. What you should think is, okay, there's an inner function here. It's x cubed, right? X cubed is in an exponent, so it's inside of another function. What's the derivative of x cubed? Well, it's 3x squared. Now, I don't quite have a 3x squared there, but I do have an x squared dx. So that should kind of remind you of, oh, we're just going to take like a 1/3 and move that outside. And this is going to proceed basically the same exact way as the power stuff from the last section did. So u is the inner function whose derivative you also see somewhere in there, maybe off by a constant. U is x cubed. You have no choice. Du is 3x squared dx. And to get that to look like x squared dx, all you have to do is divide by 3. So 1/3 du can replace all that other stuff in the integral. So that whole original complicated looking integral just becomes the integral of e to the u times 1/3 du. And you're just going to put the 1/3 out front. Okay, so that's just 1/3 that integrates to just e to the u. 1/3 e to the u plus c, and then just replace the u with what it was in the first place, which is x cubed. And check by differentiating. You can almost do that derivative in your head. Okay, it's 1/3 e to the x cubed times 3x squared. The 1/3 kills the 3. What do you got? E to the x cubed times x squared, and that's all we did. All we just did was we reversed the effects of the chain rule. So that's our old power rule. That's our first kind of big rule of integration. And it has a gaping kind of flaw in it, is if you look at that, the result of that formula on the right, if n were -1, that's a big no-no, right? Because you'd be dividing by 0. So I don't know if I said that originally, but you can see that that's true. This rule does not work universally. But it only doesn't work when n equals -1. That's the only time we're going to have a problem is, well, we'd be dividing by 0. So, easy fix. So let's just look at one that we can do with the tools that we have right now. We just haven't seen one quite like it. Okay, so 2x over x squared plus 1. You should notice, okay, the derivative of the bottom is just the top. And that x squared plus 1 really is an inner function. If you have 1 over a function, then something's being done to that function, naming it's like being reciprocaled. So the x squared plus 1 really is your inner thing. So again, that's your only candidate for your u substitution. And also its derivative appears up top, right? So that that should work, but we haven't seen one exactly like that. So here's what happens. It may be helpful to write it like that. So now it's a product. Now it's 1 over x squared plus 1 times 2x dx. So if you let your u equal x squared plus 1, all that other stuff is just du. Du is 2x dx, and you're left with the integral of just 1 over u du. And now this isn't the same thing as the power rule, so this is like our u to the negative 1, that we can't use the power rule, but you do know a function whose derivative is 1 over u. You're thinking about it, hopefully you've got it, right? Okay, it's the natural log. So it kind of swoops in out of left field to like save us because our power rule didn't work. Sometimes mathematics just has ways of kind of filling in the gaps. Let's talk about absolute values. So the integral of 1 over u du is just the natural log of the absolute value of u plus c. Again, that's, you know that, because the derivative of natural log of x is 1 over x. So this is literally just the backwards of that. We have to use the absolute value because if you look at that thing on the left-hand side, 1 over u, I can stick a negative number into that, right? I can stick negative 10 or something in for u with no problem. It's just negative 1/10. But I cannot stick a negative number into a natural log function. So think back to what logs are. They don't accept negative numbers. They have a positive base. And if you look at the graph of ln of x, it's only defined for positives. So it's not defined at 0 and it's not defined at anything negative. Now 1 over u isn't defined when u equals 0 either, so that's fine. But it's just all that negative stuff. So we want a function and its integral to have a matching domain. So it's just fixed if we just call it absolute value of u. We didn't have to do that with the derivative because you're only sticking positive numbers into a log, so it doesn't matter for its derivative. But now you can stick negative numbers into 1 over u, so it does matter for its integral. So the best way to see that is to just look at the graph. That green thing is 1 over x, right? It's just a hyperbola with an asymptote in the middle. That red thing is natural log of absolute value of x. So they both have vertical asymptotes as 0, but other than that, they're fine. Other than that, they accept all the same numbers. So by making it that red thing be absolute value, it defines it back there in negative land, and it makes those two functions have the same exact domain. So now anything we stick into 1 over u, we can also stick into its integral. Okay, and it just works. So on your little table of integral formulas, you're always going to see its absolute value of u. So don't forget to write that because it's technically wrong if you do. All right, so now it's just 1 over u du. And in our example we were doing, that integrates to natural log of absolute value of x squared plus 1, then plus c. So again, do the differentiation. So the derivative of that thing on the right-hand side is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, which is exactly what we started with, right? So again, you're just undoing the effects of the chain rule. So anytime your u is just in a denominator, you're going to use a natural log. Now, you may be thinking, hey, isn't x squared plus 1 never negative, so I actually don't need the absolute value bars? Actually, yeah, smartass, you're right. But in this specific case, but that's not always going to happen. So it doesn't hurt to put the absolute values around a positive quantity, so just do it. Just get used to doing it. If you didn't put them in this example, I could not mark it wrong. But the best strategy for you is just to always do it, okay? Very similar problem to the last one, and I'm kind of going to breeze through it because these are really all the same kind of thing. So you look at the denominator, and you think, okay, the derivative of that thing is 3x squared plus 3. Now 3x squared plus 3 isn't exactly what I have on top, but it almost is if I factor the 3 out of it. So see, it's always the same thing. The derivative also appears, maybe off by a constant, but you don't have a choice here for your u. Your u has to be that inner function, which is x cubed plus 3x plus 5, so it better work. Du 3x squared plus 3 dx So you got to make that thing look like what's on top, which is just one move. You factor a 3 out of it. You then divide that on both sides, and you have exactly what you want. You have 1/3 du equals the rest of that integral, which is x squared plus 1 dx. Now that goes in for the x squared plus 1 dx, and all you're left over with is 1 over u. Same, right? Same exact thing as the last problem. So 1/3 1 over u, that's just your natural log. So the 1/3 comes with 1/3 natural log of absolute value of u plus c, and then finally just stick to whatever u was in the first place. So that expression involving x. So it's 1/3 natural log of absolute value of x cubed plus 3x plus 5 plus c. And then that thing inside the absolute values now could absolutely be negative. So that's why I say just in general, best practice is just to put the absolute values. It's never wrong. Okay, so it looks complicated, but it's just like any of the other ones. And then just think backwards, right? Look at that thing there and think, okay, if I were going to take the derivative of that, what would happen? What would happen is just everything we just did would be undone. The 3's would cancel out, and you'd end up with what we started with. So that's how to do one where the u is just by itself in a denominator. So that essentially fills in our power rule, and now we can do any kind of integral that looks like this.